Join us as astronomers revisit one of the strangest interstellar objects ever detected, 3I Atlas. First discovered in April 2020 by the Asteroid Terrestrial-impact Last Alert System in Hawaii, 3I Atlas became only the third confirmed object to enter our solar system from interstellar space, following 1I ʻOumuamua and 2I Borisov. It traveled on a hyperbolic orbit, indicating it came from outside the Sun's gravitational influence. The constant acceleration. When the interstellar comet 3I Atlas was first detected in April 2020, astronomers immediately began calculating its trajectory. Its hyperbolic orbit, with an eccentricity of about 1.1, confirmed that the object was not gravitationally bound to the Sunday. That meant it had come from beyond our solar system, and once it passed through, it would never return. But early orbital models soon revealed something unusual, a small yet measurable deviation from the path, predicted by pure gravity alone. In celestial mechanics, a comet's motion is primarily determined by the Sun's gravitational pull. However, active comets often experience tiny additional accelerations caused by outgassing jets of vapor produced when ices on the surface sublimate under solar heat. These jets act like miniature thrusters, pushing the comet slightly off course. In the case of 3I Atlas, researchers from the Minor Planet Center, the European Space Agency, and several independent observatories noted that its trajectory fit better when a non-gravitational term was added to their models. This term was small, less than 1/10,000th of the Sun's gravitational influence, but statistically significant. It was a familiar effect. Both previous interstellar objects, 1I ʻOumuamua in 2017 and 2I divided by Borisov in 2019, had shown similar behavior. ʻOumuamua, in particular, displayed a non-gravitational acceleration that became one of the most discussed astronomical findings of the decade. But there was an important difference. Unlike ʻOumuamua, which showed no visible coma or tail, 3I Atlas exhibited clear cometary activity. It released dust, gas, and volatile compounds, the hallmarks of a typical cometary nucleus. That meant its acceleration could be explained by standard outgassing physics, not exotic mechanisms. Detailed photometric studies carried out in mid-2020 by ESO's Very Large Telescope and the Lowell Discovery Telescope helped quantify the effect. As the comet approached its perihelion, about 0.25 astronomical units from the Sun, its gas production increased sharply. The most abundant components were water vapor, H2O, carbon dioxide, CO2, and carbon monoxide, CO. When these gases escaped from the comet's surface, they produced small thrusts that slightly altered its orbit. The resulting acceleration, while measurable, was entirely consistent with known cometary dynamics. The same period saw a rapid increase in brightness, followed by a dramatic decline, which indicated fragmentation. Sometime around the 20th of May 2020, 3I Atlas likely split into several pieces. The disintegration event explained both the fluctuations in its light curve and the sudden loss of structural integrity seen in later observations. After the breakup, the main nucleus continued to emit gas and dust, which sustained minor non-gravitational forces as it retreated from the Sunday. Astronomers modeled the trajectory using the Marsden-Sacconina non-gravitational model, a standard method developed for predicting the paths of active comets. The equations included three components: radial, away from the Sun; transverse, along its orbital path; and normal, perpendicular to the orbital plane. For 3I divided by Atlas, the dominant component was radial, consistent with jet-like outgassing directed toward space. Once the model was adjusted to include this term, the residuals in the orbital fit dropped to near zero. In other words, the motion made perfect sense once cometary activity was accounted for. By the time the comet moved beyond 2 astronomical units, the activity had subsided and the acceleration decreased accordingly. Observations by the Pan-STARRS telescope in mid-2020 confirmed that the fading brightness matched expectations for a comet that had exhausted its volatile material. No evidence indicated any sustained or artificial propulsion. The changes in speed and direction were natural consequences of sublimation physics. While small, this case remains scientifically important because it provided one of the clearest examples of non-gravitational forces acting on an interstellar object. For comparison, the acceleration detected for ʻOumuamua was about 5 times 10 to the power of -6 meters per second squared, roughly equivalent to the force a sheet of paper feels from air pressure. For 3I divided by Atlas, the value was slightly lower but within the same order of magnitude. The similarity confirmed that such effects are likely common among icy bodies traveling between stars. In 2021, the NASA Center for Near-Earth Object Studies, CNEOS, released refined orbital elements that incorporated all known non-gravitational parameters. The improved model predicted the comet's outbound trajectory with remarkable accuracy, matching every available observation until the object faded beyond detection limits. As of now, 3I divided by Atlas is moving away from the Sun at roughly 42 kilometers per second, on a course that will carry it back into interstellar space, likely never to be seen again. The constant acceleration, sometimes referenced in early discussions of 3I Atlas, wasn't mysterious or unique. It was a normal, physically understood process that occurs whenever an icy nucleus releases gas unevenly. Similar forces were observed on Comet 67P, divided by Churyumov-Gerasimenko, visited by ESA's Rosetta spacecraft, where precise instruments measured jet-induced accelerations that subtly shifted the comet's orbit around the Sun. For scientists, 3I Atlas confirmed something crucial. Interstellar objects behave like their solar system counterparts, following the same physical laws. Its motion, though briefly unpredictable, was governed not by hidden mechanisms, but by sunlight, heat, and chemistry, the simple forces that shape all comets. By late 2021, 3I Atlas had faded beyond the reach of even the largest telescopes. No follow-up detections were made. Yet, its passage left a scientific legacy: precise data showing how fragile interstellar comets can be, and how their subtle accelerations can teach us about the environments in which they formed. Today, when astronomers model new interstellar candidates, they use lessons learned from 3I Atlas. Expect variability, expect outgassing, and always include non-gravitational terms in orbital equations. These refinements mean future visitors can be studied with greater precision from the moment they appear. The motion of 3I Atlas was not defiance of physics, it was physics, written in vapor and sunlight, playing out across the quiet dark of the inner solar system. Its small but steady acceleration remains one of the most precisely measured signatures of an interstellar comet in history, and a reminder that even the faintest forces can shape the vastest journeys, the breakup and disappearance. By late April 2020, astronomers already suspected that something was changing inside the interstellar comet, 3I Atlas. What began as a faint, stable point of light detected by the Atlas survey had grown brighter in early observations, consistent with increasing outgassing as it neared the Sunday. But then, within a few short weeks, its brightness began to fluctuate, irregularly fading and brightening again, with a rhythm that suggested structural instability. Such behavior wasn't unexpected. Many small comets experience internal pressure as trapped ices sublimate, forcing gas through fissures and fractures in their crust. Yet the pattern for 3I Atlas was unusually violent. The first public sign of trouble appeared in May 2020, when the European Southern Observatory, ESO, and the Gran Telescopio Canarias, GTC, in La Palma, captured high-resolution images showing the comet's core surrounded by a diffuse, elongated cloud. The nucleus appeared to have stretched, no longer a single condensed point. When the images were processed, astronomers realized that 3I divided by Atlas had begun to fragment. Several pieces, possibly 3 or more, were separating from the main body. Fragmentation is a natural end for many comets, especially those that pass close to the Sunday. Internal pressure, spin, and thermal stress can tear a weak nucleus apart. The same process was observed decades earlier with comet Shoemaker-Levy 9, which broke into more than 20 fragments before colliding with Jupiter in 1994. For 3I Atlas, however, the event occurred in open space, away from any planet's influence. The only significant force acting on it was sunlight. As the comet neared 0.25 astronomical units just inside Mercury's orbit, it began to disintegrate rapidly. Observations from multiple facilities, including Pan-STARRS and Lowell Observatory, showed that its total brightness fell by nearly 2 magnitudes in just a few days. The coma expanded, while the central condensation, the bright, concentrated nucleus, faded until it disappeared entirely. Spectroscopic analysis from the GTC confirmed that the object's gas emissions were dominated by hydroxyl, OH, a common breakdown product of water vapor, along with smaller amounts of carbon monoxide, CO, and cyanogen, CN. The presence of these volatile species was consistent with standard cometary chemistry. There were no exotic compounds or unexplained signatures. The fading spectrum indicated that 3I divided by Atlas was exhausting its volatile materials, quite literally running out of the ingredients that made it visible. By June 2020, the object was classified as fading and fragmented. Astronomers at the Minor Planet Center published updated orbital elements that treated the main nucleus as effectively gone. The estimated debris cloud spanned tens of thousands of kilometers. While some fragments may have continued along the same outbound trajectory, they quickly became too faint for detection. The final confirmed observation occurred on the 12th of June 2020, using the Las Cumbres Observatory Global Telescope Network, which recorded a diffuse smear of light at magnitude +18, barely distinguishable from background noise. After that, 3I divided by Atlas was gone. Its loss wasn't unexpected, but it was disappointing. Interstellar objects are rare opportunities. Only 3 have been confirmed so far. Once they fade, they're gone forever, their secrets carried back into the dark. For planetary scientists, however, the data collected during those brief months was invaluable. The breakup event allowed direct measurement of how an interstellar comet behaves under solar heating, information that had never before been available. Detailed analysis published in Astronomy and Astrophysics 2021 and the monthly notices of the Royal Astronomical Society 2022 confirmed that 3I divided by Atlas had a composition similar to long-period comets from the Oort cloud. Its ices were dominated by H2O, with smaller fractions of CO2 and CO, suggesting that the conditions in its home system resembled those near our own outer planets. The conclusion was striking. Even though 3I Atlas came from another star, its chemistry wasn't alien. It was familiar. That familiarity carried an important implication. The processes that form comets' condensation of ices, mixing of dust and carbon, and ejection by gravitational interactions appear to be universal. Wherever stars and planets form, nature seems to build the same kinds of icy wanderers. 3I Atlas wasn't a cosmic anomaly. It was a confirmation that our solar system isn't unique in the way it produces small bodies. The data also revealed that the fragmentation itself was likely triggered by rotational spin-up, the gradual acceleration of a comet's rotation caused by uneven outgassing. As gas vents from the surface, it produces tiny torques that can increase the spin rate over time. Once the centrifugal force exceeds the weak structural cohesion of the nucleus, the comet breaks apart. Models suggested that 3I Atlas's rotation period may have dropped below 2 hours just before its final disruption, enough to tear it open. Although its fragments were lost, astronomers continued to monitor its debris trail through 2021 using wide-field surveys like Pan-STARRS and Zwicky Transient Facility, ZTF. None of the expected dust or residual fragments were detected. The event had been total. By all accounts, the comet had disintegrated completely, its materials dispersed into the interplanetary medium. Today, only its orbital parameters remain. The trajectory of 3I Atlas is well defined. An inbound speed of 44 kilometers per second, a perihelion distance of 0.25 AU, and an outbound vector that carries it toward the constellation Lyra. It will continue traveling through the galaxy, but what was once a solid nucleus is now a faint cloud of microscopic particles, invisible to any telescope. In the end, 3I Atlas didn't survive its visit, but it left behind something just as valuable: a detailed record of how interstellar material behaves under solar radiation. The brightness curves, spectral data, and orbital measurements collected during its breakup remain part of public archives, accessible to researchers studying the chemistry and mechanics of small bodies. Every observation helped refine our understanding of what interstellar comets are made of and how fragile they can be. When it was first discovered, 3I Atlas was celebrated as another chance to study a traveler from beyond the stars. Its disintegration was a reminder that such opportunities are fleeting. These objects arrive unannounced, linger for months, and vanish forever, carrying with them the physical history of distant worlds. In the story of interstellar exploration, 3I Atlas stands as both a brief encounter and a scientific landmark proof that even in loss, a comet can illuminate what connects one star system to another. Comparing the three interstellar visitors. When astronomers talk about interstellar visitors, they're referring to a class of objects so rare that, to date, only 3 have been confirmed. They are 1. ʻOumuamua, discovered in 2017, 2. divided by Borisov in 2019, and 3. IATLAS in 2020. Each passed through our solar system briefly, following a hyperbolic orbit, the unmistakable signature of something not born under the sun's gravity. Together, they've rewritten what we know about how planetary systems form and how debris moves between the stars. The story began with ʻOumuamua, detected by the Pan-STARRS telescope in Hawaii on the 19th of October 2017. It became the first confirmed object of interstellar origin ever observed. Its orbit had an eccentricity of 1.2, far beyond any comet or asteroid bound to the Sun. It approached from the direction of the constellation Lyra, passed within 0.25 astronomical units of the Sun, and exited the solar system at roughly 26 kilometers per second. But what drew the world's attention wasn't its speed, it was its behavior. ʻOumuamua displayed no visible coma, no dust tail, and no sign of outgassing. Yet its trajectory showed a small, continuous acceleration, not explained by gravity alone. Normally, such a force would be attributed to sublimating gases as with comets, but spectroscopy found nothing. Instead, the object remained dark and inert, with a slightly reddish hue similar to organic-rich asteroids. Its light curve, the variation in brightness as it rotated, suggested a highly elongated shape, possibly 400 meters long and only 40 meters wide. Astronomers proposed natural explanations: a fragment of a larger body, a dense hydrogen iceberg, or even a thin, pancake-like shard of nitrogen ice. Others, including a 2021 Harvard study, raised the possibility of a thin reflective object, though no evidence supported that idea. What mattered most was that ʻOumuamua showed that solid interstellar debris exists, material ejected from other star systems that can travel for millions of years before briefly crossing ours. 2 years later, the discovery of 2I divided by Borisov by amateur astronomer Gennady Borisov in August 2019 provided the first chance to compare. Unlike ʻOumuamua, Borisov was unmistakably a comet. Its appearance, a bright coma and a clear dust tail, was typical of volatile-rich bodies that heat up near stars. It followed a hyperbolic path with an eccentricity of 3.36, approaching the Sun from the direction of Cassiopeia. Its inbound speed was about 32 kilometers per second relative to the Sun, slightly higher than typical Oort cloud comets, but consistent with interstellar motion. Spectroscopic data collected by the Hubble Space Telescope, ALMA, and the Very Large Telescope revealed that 2I Borisov's composition was surprisingly ordinary. It contained water ice, carbon monoxide, and complex organic molecules, the same substances found in solar system comets. However, one detail stood out. Borisov contained an unusually high ratio of CO to H2O, indicating it had formed in a colder environment, possibly farther from its parent star than most of our comets do. That single measurement revealed that other planetary systems likely produce icy bodies under a wide range of conditions, some even more extreme than our Kuiper Belt. By the time 3I Atlas was detected in April 2020, astronomers already had a framework for studying interstellar visitors. Its trajectory and brightness matched expectations for a small, active comet entering from interstellar space. Like Borisov, it showed a coma and faint tail, confirming the presence of volatile materials. Photometric analysis estimated its nucleus at roughly 100 meters in diameter, comparable to small solar system comets. The key difference was its fragility. 3I Atlas disintegrated before reaching perihelion, an event well documented by telescopes in Hawaii, Chile, and the Canary Islands. Unlike Borisov, which survived its solar passage intact, Atlas broke apart under thermal stress. The likely cause was a combination of internal gas pressure and spin-up, a gradual increase in rotation caused by uneven outgassing. By May 2020, its nucleus had fragmented into several smaller pieces, which quickly faded from view. The comet's light curve dropped sharply, and by June, it was gone. From a scientific standpoint, these three interstellar objects form a natural progression. ʻOumuamua showed that rocky or dense interstellar fragments exist. Borisov proved that volatile, rich, comet-like bodies exist outside our solar system. And Atlas demonstrated how fragile such visitors can be when they enter the intense heat of another star's inner system. Together, they also highlight the variety of materials and conditions found in other planetary systems. Borisov's cold chemistry and high CO content point to a formation zone far from its star, perhaps an analog to our own Oort cloud. ʻOumuamua's dry, reflective surface suggests the opposite, a fragment from a rocky world, or a dense, carbon-rich layer. Atlas, with its rapid breakup, may represent a middle ground, an icy body loosely held together, possibly ejected early in its home system's formation. In all three cases, the mechanics of ejection are thought to be the same. During the early stages of planet formation, gravitational encounters with giant planets can fling smaller bodies into interstellar space. Over billions of years, those ejected fragments drift through the galaxy, occasionally passing through other star systems, including ours. The sheer diversity between these three visitors implies that every planetary system contributes differently to this cosmic traffic. Statistically, models now suggest that hundreds of interstellar objects pass through our solar system every year. Most are too small or faint to detect, but wide-field surveys like Pan-STARRS, ATLAS, and ZTF are improving the odds. In 2023, researchers using the Vera C. Rubin Observatory projected that its next-generation survey could detect several interstellar objects each decade. Each detection refines our understanding of the galactic environment not through radio signals or spacecraft, but through drifting debris. While none of these objects can be visited directly, their trajectories and spectra already tell us more than decades of indirect modeling. They confirm that the Milky Way shares a common chemistry. Water, carbon compounds, silicates, and ices appear universal. They also reveal that the boundaries between star systems are not empty, but filled with the remnants of creation, small travelers, billions of years old, crossing between suns. ʻOumuamua taught us to expect the unexpected. Borisov showed us that the familiar exists even in the alien. Atlas reminded us that some stories end before we can finish reading them. Three objects, three glimpses into other worlds, each one brief, each one final. But together, they form a map, not of space, but of connection. Evidence that the matter that builds planets here also wanders endlessly between the stars. How interstellar comets are ejected. Every interstellar comet begins as something ordinary, a piece of ice and rock orbiting a young star. The difference between a comet that stays and one that leaves forever comes down to gravity, motion, and chance. The process that launches these objects into the galaxy starts billions of years before they ever cross our skies. In the early stages of a planetary system's formation, a protoplanetary disk surrounds a new star, a flat, rotating plane of dust, gas, and ice. Within this disk, particles collide and merge, forming larger bodies known as planetesimals. Over millions of years, some grow into planets, while others remain smaller, orbiting on the system's outer edges. These distant bodies become reservoirs of icy debris, the raw material for future comets. In our solar system, that reservoir is known as the Oort cloud, extending nearly a light year from the Sunday. The same process happens around other stars. But in every system, the presence of giant planets, Jupiter-like worlds with immense gravity, changes everything. As they form and migrate through the disk, their gravitational influence acts like a slingshot. When smaller icy bodies stray too close, they are either pulled inward toward the star or flung outward into deep space. Those that reach escape velocity leave their system entirely, becoming what astronomers call interstellar objects. Simulations of early planetary systems, including those conducted with NASA's Planetary Dynamics Code and the Rebound N-body integrator, show how efficient this mechanism can be. A single Jupiter-mass planet can eject millions of comet-sized bodies during its lifetime. Over billions of years, these ejections accumulate, populating the galaxy with countless fragments traveling between the stars. Most remain invisible, drifting cold and dark through interstellar space. But occasionally, one of them passes close enough to another star ours, for example, to be detected. The key physics behind this ejection process are simple. When a smaller body encounters a much larger one, energy and momentum are exchanged. If the geometry is right, the smaller object gains velocity relative to the central star, often far exceeding the system's escape speed. In the solar system, this same principle allows spacecraft to perform gravitational assists, using planetary flybys to increase their speed without burning fuel. In the case of comets, it's a natural version of that maneuver, a one-time acceleration that ends with permanent exile. Astronomers believe that both 1I, ʻOumuamua, and 2I, divided by Borisov, were created this way. Their inbound speeds and directions suggest they were ejected from star systems within a few hundred light-years of Earth, possibly during the chaotic phase of planetary migration. Theoretical work by Sean Raymond and Dmitry Veras in 2018 estimated that every star in the Milky Way could eject between 10 to the power of 13 and 10 to the power of 16 cometary bodies during its lifetime. That's roughly a quadrillion objects per star, a vast interstellar population drifting unseen between the stars. When these bodies leave their parent systems, they enter interstellar space, an environment colder and emptier than any vacuum on Earth. Temperatures fall to just a few degrees above absolute zero, preserving their volatile materials for millions or even billions of years. Over time, cosmic rays darken their surfaces, producing the reddish tint seen on many distant asteroids and on ʻOumuamua itself. These space-weathered coatings act like armor, sealing the ices beneath from further loss until the object encounters a new star. When that happens, the story begins again. As the object falls inward toward the new star's light, the heat reverses millions of years of freezing. Ices sublimate, gases vent, and the familiar coma and tail appear, the signature of an active comet. This transition explains why 2I Borisov brightened so dramatically in 2019 as it approached the Sun, while ʻOumuamua, likely depleted of surface volatiles, remained inert. The difference lies in age and composition. Borisov was a comet in the classical sense. ʻOumuamua may have been the stripped fragment of a larger, long-dead body. In 2020, when 3I Atlas was detected, its path confirmed the same story: a hyperbolic orbit with an eccentricity greater than 1, meaning it was not bound to the Sunday. The likely cause of its ejection mirrored that of countless others: gravitational scattering in its birth system. Once flung free, it traveled for eons through interstellar space, until, by chance, it intersected Earth's neighborhood. This mechanism, ejection by planetary interaction, is supported by both observation and simulation. In 2021, researchers from the University of Cambridge ran over 10 million computer models of young planetary systems. Nearly all showed that once a giant planet forms, ejections become inevitable. Within just 100 million years, more than half of all outer comets are expelled. The survivors remain as Oort clouds. The rest become wanderers between the stars. Because these ejected bodies are small and dark, detecting them is extraordinarily difficult. ʻOumuamua was visible for only a few weeks, 2I Borisov for less than a year, and 3I ATLS for just a few months before disintegrating. Their discovery rates match the expectations of current survey sensitivity, meaning there are likely billions of others passing unnoticed through the solar system each century. Future wide-field observatories, especially the Vera C. Rubin Observatory and its Legacy Survey of Space and Time, LSST, are expected to increase detections dramatically. LSST's design scanning the entire sky every few nights with a 3.2 gigapixel camera may capture several interstellar objects per decade. Each new detection adds another piece to the puzzle of galactic formation. By analyzing their compositions, astronomers can infer the temperature and chemistry of their birth environments. A comet rich in carbon monoxide, like Borisov, likely formed in a very cold region. A dry, rocky object like ʻOumuamua may have formed closer to its star. Over time, these comparisons build a map not of geography, but of origin, showing how matter circulates between systems. In a galaxy of over 400 billion stars, the ejection of comets is not an exception but a rule. Every planetary system produces them. Every system loses them. Each one that crosses our path is a piece of another solar system's history, preserved in ice and dust. When 3I Atlas disintegrated near the Sun in 2020, it was not the end of its story. Its fragments continued outward, carrying the same atoms that once orbited a star hundreds of trillions of kilometers away. Somewhere in the galaxy, other systems are doing the same, ejecting their own small messengers into the dark, bound for no destination, but destined to remind whoever finds them that the Milky Way is not a collection of separate worlds. It is a single system of shared debris, connected by motion, and shaped by the same gravitational dance that began the first time a planet formed around a star. The search for the next interstellar visitor. Since 2017, when the first interstellar object was discovered, astronomers have known one thing for certain: there are more of them out there. The challenge is not their existence, but their detection. Interstellar visitors are faint, fast, and brief. They cross our solar system in months, sometimes weeks, before disappearing forever. The search for the next one, the future 4I, 5I, and beyond, depends on how quickly and how clearly we can see the sky. Current evidence suggests that interstellar objects pass through the solar system regularly, possibly several times each year. Theoretical models by the Harvard-Smithsonian Center for Astrophysics and the University of Cambridge estimate that thousands of comet-sized bodies travel through the inner solar system over the course of a millennium. Most go unnoticed, simply because they are too small or too dark to reflect enough light for detection. To catch the next one, astronomers are turning to a new generation of telescopes, designed not for deep, narrow imaging, but for wide-field, continuous surveys. These systems scan enormous sections of the sky every night, building a dynamic record of everything that moves. At the center of this new search is the Vera C. Rubin Observatory, under construction in Chile's Atacama Desert, scheduled to begin full operations in 2026. Rubin's Legacy Survey of Space and Time, LSST, will image the entire visible sky every 3 to 4 nights, using the world's largest digital camera, a 3.2 gigapixel sensor capable of detecting objects as faint as magnitude 24.5. Unlike traditional observatories that focus on specific targets, Rubin will produce a continuous, evolving map of the night sky. This data will allow astronomers to identify new objects by comparing sequential images and tracking their movement. Because interstellar objects travel on hyperbolic orbits, faster and more curved than local asteroids, their trajectories stand out immediately in motion analysis. Rubin's high cadence and computational power will make it possible to identify candidates in near real time, allowing follow-up telescopes to begin tracking within hours instead of weeks. NASA's upcoming NEO Surveyor mission, set for launch in 2027, will complement this effort from space. Operating in infrared wavelengths, it will detect the heat signatures of small bodies that are invisible in optical light. Interstellar visitors, especially those rich in volatiles like 2I Borisov, emit faint infrared radiation as they warm near the sunday. By combining data from Rubin and NEO Surveyor, astronomers will gain a complete view: visible light for motion, infrared for composition. This dual approach is expected to increase detection efficiency dramatically. Even now, ongoing surveys are preparing the ground. The Pan-STARR system in Hawaii, the Zwicky Transient Facility, ZTF, in California, and the Atlas network continue to scan the sky nightly, detecting near-Earth objects and fast-moving transients. These systems discovered all 3 known interstellar visitors so far: 1I, ʻOumuamua, by pan-stars, 2I divided by Borisov, by an amateur using similar wide-field optics, and 3I divided by Atlas, by the Atlas survey itself. Each discovery has guided the next step. The upcoming Rubin Observatory is expected to go much further. Its survey will cover 18,000 square degrees of sky with each cycle, producing roughly 20 terabytes of data per night. Automated detection algorithms will analyze motion patterns, comparing observed tracks against known orbits of asteroids and comets. Any object deviating significantly, especially those with hyperbolic eccentricities greater than 1, will be flagged for immediate verification. It is estimated that Rubin could discover one new interstellar object every few years, possibly the first dozen within its 10-year operational window. Once a candidate is found, rapid response observatories will take over. The Very Large Telescope, VLT in Chile, Keck Observatory in Hawaii, and the James Webb Space Telescope, JWST, will analyze its spectrum to identify ices, dust, and organic compounds. If the object is bright enough, its rotation period and shape can be inferred from light curve measurements, the same method used to model ʻOumuamua's elongated form. For active comets, ultraviolet and infrared spectroscopy will reveal their composition in precise molecular detail. Beyond observation, space agencies are already planning for direct missions. In 2023, the European Space Agency (ESA) selected the Comet Interceptor mission, designed to wait in orbit at the Sun-Earth L2 point until a new comet or interstellar object is discovered. When a target is confirmed, the spacecraft will launch on a trajectory to intercept it. Its goal is simple: study a pristine, untouched object before it's altered by solar heat. If an interstellar visitor is identified early enough, Comet Interceptor could become humanity's first close-up encounter with material from another star system. The science behind these missions is more than curiosity. Interstellar objects offer a direct way to study the formation and evolution of planetary systems across the galaxy. Their chemistry preserves the conditions of their birth environments, pressures, temperatures, and compositions that can't be replicated in laboratories. Measuring those differences tells us how common our solar system really is. If most interstellar comets share similar ices and organics, it suggests the Milky Way builds planets under consistent rules. If not, it means our system is only one of many possible blueprints. Each discovery also improves our understanding of planetary defense. By comparing how interstellar bodies differ from native asteroids, researchers can refine impact models and improve early warning systems for fast-moving near-Earth objects. The same algorithms that identify interstellar visitors can also spot potential hazards weeks or months earlier than before. Ultimately, the search for the next interstellar visitor is more than a technical challenge, it's a test of awareness. Every object like ʻOumuamua or Borisov is a messenger, carrying the story of another star system. Their paths are brief, but their data endures. As the Vera C. Rubin Observatory begins its full sky survey and NASA's NEO surveyor takes its place in orbit, astronomers expect a new age of discovery, one where interstellar visitors will no longer be once-in-a-lifetime events, but regular guests on their endless journeys through the galaxy. And when the next one comes, whether it's 4I, 5I, or beyond, the instruments will be ready, and so will we. For the first time in history, humanity will not just watch an interstellar traveler pass by. We will meet it, study it, and perhaps finally understand where it came from. What interstellar objects reveal about planet formation. When the first interstellar object crossed our solar system in 2017, it wasn't just a curiosity, it was a revelation. For the first time, scientists could study material that had formed around another star. Until then, everything we knew about planetary systems came from either direct observation of distant exoplanets or from our own neighborhood. 1I ʻOumuamua, 2I Borisov, and 3I Atlas changed that. They offered, quite literally, pieces of another world. The importance of these visitors lies in what they represent: unaltered fragments of planetary formation processes that took place light years away. Each interstellar object is a sample of its home system's history, a physical record of how other stars built their planets. Studying them helps answer a fundamental question in astronomy: Is our solar system typical or unique? In the case of 2I Borisov, the answer began to take shape. Spectral analysis by the Atacama Large Millimeter, divided by submillimeter array, ʻOumuamua, revealed that its coma contained unusually high levels of carbon monoxide, CO, relative to water, H2O. In solar system comets, that ratio is typically much lower, because water dominates and carbon monoxide only becomes stable in extremely cold regions. Borisov's CO divided by H2O ratio was about 9 times higher than in most Oort cloud comets. That one measurement told scientists that the comet must have formed farther from its parent star, in a region of deep freeze where sunlight never reached. That composition matters, because it directly links to where and how planets form. In the outer regions of a protoplanetary disk, molecules like carbon monoxide and methane condense at lower temperatures, creating ice-rich planetesimals. The high CO content of Borisov implies that its home system had a cold, extended disk, possibly larger than our own. It suggests that gas giants in that system may have formed farther out, or that the disk retained volatile materials longer than ours did. On the other hand, 1I ʻOumuamua painted a very different picture. It showed no detectable outgassing, no coma, and no visible tail, yet it still experienced a tiny non-gravitational acceleration. The lack of typical cometary activity led astronomers to suspect that ʻOumuamua was composed of dense, refractory materials similar to the crusts of rocky bodies rather than the icy cores of comets. Several studies proposed it could be a fragment of a larger planetesimal, possibly broken off during a collision in its home system, and later ejected. Its reddish surface color matched that of irradiated organic compounds, suggesting long exposure to cosmic rays during interstellar travel. These two visitors, Borisov, the volatile rich comet, and ʻOumuamua, the dry fragment, together demonstrate the diversity of materials produced by planetary systems. Some form cold and soft, others dense and durable. Their coexistence in interstellar space proves that other stars go through the same chaotic processes we see evidence of in our own past: collisions, ejections, and the scattering of debris by newly formed planets. When 3I Atlas arrived in 2020, it fit this growing pattern. It resembled Borisov more than ʻOumuamua, an active comet that produced a coma, released gas, and ultimately disintegrated under solar heating. Spectroscopic data collected before its breakup identified familiar signatures of hydroxyl radicals, OH, cyanogen, CN, and diatomic carbon, C2, all common in solar system comets. That chemical similarity reinforced an emerging conclusion: the chemistry of planetary formation is not unique to the Sunday. Across the galaxy, stars appear to produce comets from the same basic elements: water, carbon, oxygen, nitrogen, and silicon, combined in varying proportions. These results align with data from ʻOumuamua and the James Webb Space Telescope, which have observed dozens of protoplanetary disks around young stars. In every case, astronomers see the same molecular fingerprints: water vapor, carbon monoxide, hydrogen cyanide, methane, and silicate dust. The identical chemistry observed in 2I divided by Borisov and 3I Atlas confirms that the ingredients of life and the building blocks of planets are not rare exceptions. They are common features of stellar evolution. Another key insight from interstellar objects is how they record the dynamics of their home systems. The very fact that these bodies were ejected indicates the presence of large planets capable of gravitational scattering. This tells scientists that many planetary systems undergo a period of intense instability early in their history, when young gas giants migrate and interact. In our own solar system, that stage is thought to have occurred about 4 billion years ago, during the so-called nice model phase, when Jupiter and Saturn's shifting orbits ejected vast numbers of comets into the Oort cloud. The same process, scaled across billions of stars, populates the galaxy with wanderers like ʻOumuamua and Borisov. In other words, the existence of interstellar objects provides indirect but powerful evidence that planet formation is universal. If every system with giant planets ejects debris, and if we detect those fragments here, it follows that planetary formation is not an isolated phenomenon, it's a galactic constant. These travelers also teach us about longevity. Spectroscopic and thermal analyses show that interstellar comets can survive for tens or even hundreds of millions of years in deep space. Cosmic rays darken their surfaces, but their cores remain chemically stable. When such objects enter a new stellar system, their ices sublimate and release trapped materials, effectively reenacting their formation chemistry. That makes each one a natural time capsule, preserving conditions from another system's earliest moments. Future missions will make this research even more direct. Within the next 2 decades, scientists expect to move from chance observations to deliberate study, from fleeting images of faint points of light to direct encounters, detailed spectra, and eventually, physical samples. Every mission, from Rubin's nightly sky sweeps to Webb's infrared precision, is a step toward that goal. For now, the interstellar frontier remains quiet, but the instruments are ready. The sky is under constant watch, and the next messenger could appear at any time, a brief trace of motion against the stars, the next fragment of another world passing through ours. When it does, we'll be waiting not with questions of mystery, but with the tools to finally answer them. What these visitors mean for life beyond Earth. When interstellar objects first entered our solar system, the discoveries were celebrated for their rarity, fragments of distant systems passing briefly through ours. But as data accumulated, astronomers began to realize that these travelers carried something more profound than orbital information. They carried chemistry, the same molecules that form planets, oceans, and potentially life. For decades, the study of life's origins has rested on a single principle: that complex organic molecules can form naturally wherever carbon, hydrogen, nitrogen, and oxygen exist under the right conditions. These ingredients are not rare. They are abundant throughout the galaxy, found in comets, asteroids, molecular clouds, and even interstellar dust. The arrival of Borisov in 2019 confirmed this universality in a way that no previous observation could. Spectroscopic data from ʻOumuamua and the Hubble Space Telescope showed that Borisov contained cyanide, CN, formaldehyde, H2CO, methanol, CH3OH, and carbon monoxide, CO molecules, central to organic chemistry. These are the same compounds detected in comets from our own Oort cloud. Their presence in an object from another star system demonstrated that the chemical building blocks of life are not limited to the solar system. They appear to be a natural consequence of star and planet formation everywhere. What makes this discovery so significant is not just that these molecules exist, but that they survive interstellar travel. Between the stars, radiation is intense. Temperatures approach absolute zero, and collisions are rare. Yet even after millions of years drifting through this environment, Borisov still carried intact volatile compounds. This resilience implies that such materials could be exchanged between planetary systems, carried by comets and fragments like Borisov across vast distances. The idea that life's building blocks, or even microbial life itself, could travel through space is known as panspermia. It remains an open question rather than a confirmed mechanism, but interstellar objects have given it new credibility. In 2020, researchers at the Japan Aerospace Exploration Agency (JAXA) demonstrated that certain amino acids and simple sugars can survive long-term exposure to vacuum and radiation when embedded in comet-like ices. If organic compounds can persist through interstellar space, and if comets regularly pass between systems, the exchange of prebiotic material may be inevitable. On Earth, evidence suggests that comets and asteroids contributed much of our planet's carbon and water. Isotopic studies of hydrogen in terrestrial oceans closely match the ratios found in cometary ices, particularly from Comet 67P, divided by Churyumov-Gerasimenko, visited by ESA's Rosetta spacecraft. The same process could occur on other worlds. Impacts from icy bodies, delivering essential volatiles and organic compounds to young, rocky planets. If interstellar comets like Borisov and Atlas carry similar materials, they may serve as agents of chemical distribution across the Milky Way. The survival of these molecules over such immense timescales also sheds light on the early stages of life's chemistry. Laboratory experiments, such as those performed in NASA's Ames Research Center, show that UV radiation acting on ices containing carbon monoxide, methane, and ammonia can produce amino acids and nucleobases, the precursors to proteins and DNA. If these reactions occur within the dense regions of protoplanetary disks, the resulting compounds could be trapped inside comets, preserved for billions of years, and later delivered to forming planets. Interstellar comets are, in effect, natural laboratories, carriers of prebiotic chemistry, from one generation of stars to the next. The detection of similar compounds in 3I Atlas, before its disintegration, supports this view. Although the comet was faint and short-lived, its spectrum revealed hydroxyl radicals, OH cyanogen, CN, and diatomic carbon, C2, all products of organic breakdown in sunlight. These are the same species observed in solar system comets. Their repetition across unrelated systems reinforces the idea that organic chemistry is a cosmic standard, not an exception. Astronomers are now exploring how often these chemical carriers might intersect with habitable worlds. Using data from the European Space Agency's Gaia mission, researchers have modeled how interstellar comets move through the galaxy and how frequently they might enter planetary systems like ours. The results suggest that billions of such objects could be drifting through the Milky Way at any moment. Statistically, a significant number would pass close enough to deposit dust and volatile material on planetary atmospheres. This idea does not claim that life itself travels between stars only, that the ingredients of life do. The presence of amino acids in meteorites found on Earth, such as the Murchison meteorite, proves that complex organic compounds can form in space and survive atmospheric entry. Interstellar comets extend that principle beyond our solar system. If similar impacts occur elsewhere, then the chemistry that leads to biology could be seeded across many worlds independently. Future missions aim to test these possibilities directly. ESA's Comet Interceptor, set to launch later this decade, may one day encounter an interstellar comet and analyze its material firsthand. Instruments aboard the spacecraft will measure isotopic ratios of carbon, nitrogen, and hydrogen signatures that reveal whether the organic matter it carries formed under the same conditions as ours or under entirely different ones. Meanwhile, the James Webb Space Telescope continues to observe the chemical composition of protoplanetary disks, detecting molecules such as acetylene, C2H2, and formic acid HCOOH species essential to prebiotic chemistry. The presence of these compounds around young stars supports what interstellar comets have shown us. The raw materials for life are built into the fabric of star formation itself. What emerges from this growing body of evidence is a simple but profound picture. Life, or at least the chemistry that makes life possible, does not require unique circumstances. It arises naturally wherever carbon, water, and energy coexist. Interstellar visitors like Borisov and Atlas confirm that such chemistry is widespread, not confined to one planet, one star, or one time. When we study these travelers, we are not just learning about distant systems. We are glimpsing the processes that once operated here, around the newborn sun, more than 4 billion years ago. Every molecule they carry, every fragment of ice or dust, is a piece of a story that began before Earth existed, in the search for life beyond Earth. Interstellar comets are not the answer. They are the evidence that the question itself is universal. Unfortunately, the comet's rapid fragmentation in May 2020 ended detailed analysis. Its nucleus broke apart before high-resolution spectroscopy could be completed, leaving only partial data. But even those incomplete spectra were enough to confirm that Atlas was chemically ordinary, a crucial result in itself. Like Borisov, it showed that comets from other systems share the same fundamental ingredients: water, carbon, oxygen, and nitrogen. These similarities are consistent with what astronomers observe in protoplanetary disks. Using ALMA and the James Webb Space Telescope, scientists have detected the same molecules CO, H2O, CH3OH, and HCN in disks around young stars such as TW Hydrae and HL Tau. The alignment between these remote observations and the direct chemical data from interstellar comets supports one of the strongest conclusions in modern astronomy, that the molecular composition of star-forming material is universal. How these molecules form is also well understood. In the cold regions of molecular clouds, dust grains act as chemical reactors. At temperatures below 50 Kelvin, simple atoms and radicals hydrogen, carbon, nitrogen, and oxygen condense on the surfaces of these grains and react to form ices. Ultraviolet radiation and cosmic rays then drive additional reactions, creating more complex species such as formaldehyde, methanol, and amino acid precursors. When stars form, this chemistry becomes locked into the icy planetesimals that orbit them. If those bodies are later ejected, they carry their chemistry into interstellar space preserved for millions of years, until by chance, one passes near another star. The consistency of these findings across different instruments and objects has strengthened astronomers' confidence in a key principle. The chemistry of life's precursors is not local, it's cosmic. Whether in the disks of other stars or in comets passing through our solar system, the same molecules appear again and again. Hydrogen cyanide, carbon monoxide, methanol, water, all form naturally from the same physical laws, acting on the same elements in every corner of the galaxy. Future missions will take this chemistry from detection to direct sampling. ESA's Comet Interceptor will carry spectrometers designed to measure isotopic ratios, subtle differences in the mass of elements, like hydrogen and nitrogen, that reveal the temperatures and pressures of their formation environments. Comparing those ratios across multiple interstellar comets will show whether their chemistry follows one pattern or many. If their isotopic signatures are similar, it would confirm that the processes that shaped our solar system's comets are widespread across the Milky Way. If they differ, it would mean each system carries its own chemical fingerprint, a diversity written in the atomic fabric of ice and dust. In the end, the chemistry inside interstellar comets tells a single, elegant story. The molecules that build planets, atmospheres, and potentially life itself are not rare or isolated. They are byproducts of cosmic evolution repeated across stars, across time, and across the galaxy. When we analyze the faint spectra of comets like Borisov and Atlas, we are not just observing chemistry from another system. We are looking at the common language of matter, the same patterns of carbon and water that connect every world, everywhere, to the same origin. The journey through interstellar space. When a comet is ejected from its home system, its journey has only just begun. What follows is a crossing so vast and silent that even light takes years to describe it, a voyage through the empty regions between stars, where heat, air, and direction no longer exist. Every interstellar object that reaches us from ʻOumuamua to Borisov to Atlas has survived this journey, carrying the physical memory of another star's creation across millions, perhaps billions of years. Once free of its parent star's gravity, an interstellar comet enters the interstellar medium, ISM, a space that seems empty, but is not. It is filled with tenuous gas, dust, and the faint traces of cosmic radiation. On average, a cubic centimeter of the ISM contains just one atom of hydrogen, scattered across unimaginable distances. The temperatures hover near 3 Kelvin, only a few degrees above absolute zero. In this cold and rarefied environment, motion continues forever. There are no collisions, no friction, no resistance, only the gradual shaping of matter by time and radiation. The greatest threat to an interstellar traveler is not impact, but cosmic rays. These are high-energy particles, mostly protons, accelerated by supernova explosions and the magnetic fields of galaxies. Traveling at nearly the speed of light, they bombard the surfaces of comets and asteroids, breaking molecular bonds and altering the chemistry of their outer layers. Over millions of years, this exposure forms a thin, dark crust of irradiated organic material, known as a radiation mantle. It's this process that gives many outer solar system bodies, and likely, ʻOumuamua, their reddish color. Laboratory experiments on analog materials, mixtures of methane, ammonia, and water ice, confirm that continuous cosmic ray exposure creates complex carbon chains called tholins, which absorb blue light and reflect red. Beneath that protective crust, the interior remains almost completely preserved. Even after tens of millions of years, the ice below the radiation layer remains chemically stable. Thermal modeling shows that the penetration depth of cosmic rays is limited to just a few centimeters. meaning the core of an interstellar object can stay intact for eons. This explains how 2I divided by Borisov, despite its long journey, still contained abundant volatile gases like carbon monoxide and hydrogen cyanide molecules that would have sublimated long ago if exposed. For objects ejected from their home systems, velocities vary widely. Most simulations show that comets are launched at speeds between 1 and 10 kilometers per second relative to their parent stars. Over time, they become part of the galactic population, moving with the general rotation of the Milky Way. Their orbits around the galactic center are vast, taking hundreds of millions of years to complete. Occasionally, gravitational interactions with other stars or giant molecular clouds alter their paths, sending them wandering through new regions of space. The Milky Way itself acts as a great conveyor, a system in constant motion. Every star, including the Sun, moves through the local standard of rest, carrying its own cloud of dust and debris. From our perspective, interstellar objects seem to enter from random directions, but their velocities are not chaotic. They trace the motion of the local stellar neighborhood, a cluster of stars moving together through the galaxy. Both ʻOumuamua and Borisov approached from similar galactic longitudes, consistent with this shared motion. In deep space, thermal conditions are so extreme that almost no sublimation occurs. Temperatures of 3 to 10 Kelvin mean that even the most volatile ices, such as carbon monoxide, remain frozen. Without sunlight or friction, there is no source of heat to drive chemical change. The only transformations come from radiation slow, cumulative, and surface deep. For this reason, interstellar comets are preservation capsules, holding the molecular record of their formation environments, nearly unchanged since their ejection. Occasionally, as they drift through denser interstellar clouds, they may encounter dust or weak magnetic fields. Over time, such interactions can deposit trace materials on their surfaces, thin coatings of silicate grains or carbonaceous dust. But these effects are minimal compared to what happens when they enter a new stellar system. That's when everything changes. As an interstellar comet approaches a star like the Sun, its long dormancy ends abruptly. Even at distances of 5 astronomical units, sunlight begins to warm the surface. Temperatures rise just enough for ices to sublimate, and the first jets of vapor erupt through cracks in the crust. The thin radiation mantle fractures, exposing fresh material. Gas escapes, carrying dust into space, forming the bright coma and tail we recognize as a comet's signature. This transition is exactly what astronomers observed with 2I Borisov. As it neared the Sun in late 2019, its brightness increased sharply, revealing a nucleus roughly 1 kilometer wide. The presence of CO and HCN emissions confirmed that the object had preserved volatile compounds since its formation, proof that interstellar travel had not erased its chemistry. For scientists, this was the clearest demonstration yet that organic-rich ices can survive indefinitely in interstellar space. The same evidence applies, though indirectly, to 3I Atlas. Its early spectral signatures of water and cyanide before disintegration show that even small, fragile objects can endure long enough to carry their volatiles across the gulf between stars. These comets act as emissaries of continuity, their compositions linking the chemistry of distant systems with our own. Astrophysical models suggest that within the Milky Way, there may be hundreds of trillions of such bodies, icy planetesimals, drifting silently through interstellar space. Most are invisible, their paths never crossing a star. But over billions of years, gravitational encounters ensure that some inevitably do. When they enter new systems, they release their ancient gases, mixing their chemistry with the newborn comets of those stars. This slow, quiet exchange may be one of the ways the galaxy distributes its molecular inventory, a natural process of cosmic recycling that connects stellar generations. From a dynamical perspective, the odds of any given interstellar comet entering a habitable zone are extremely low, but across galactic timescales, those odds become meaningful. If even a small fraction of these travelers intersect with young, volatile-rich planets, they could deposit carbon, water, and nitrogen compounds that help shape early atmospheres. The idea remains theoretical, but the evidence from Borisov supports its plausibility. If such chemistry survives the cold, it can also survive impact. As the Sun moves through the Milky Way, it will continue to encounter more of these silent messengers. Each one tells the same story, that space between stars is not empty, but full of relics, remnants, and travelers, still carrying the fingerprints of other worlds. Their journeys are long beyond comprehension, but their arrival here, however brief, gives us a glimpse into the shared fabric of galactic evolution. ʻOumuamua may have been a fragment, Borisov a comet, Atlas a disintegrating survivor, but all are part of the same process. Matter and motion cycling endlessly between stars. The radiation that darkens their surfaces also preserves their cores. The cold that freezes them also protects their chemistry. In every way that matters, the journey through interstellar space is not decay, it's preservation. The next time one appears, crossing our sky for a few weeks before vanishing again, it will bring with it not mystery, but memory, a record of light years traveled, of suns long gone, and of the simple, enduring fact that what is born around one star can find its way, intact, to another. To calculate these motions, astronomers rely on precise astrometry, the measurement of position down to fractions of an arcsecond. Instruments like the Gaia spacecraft provide the reference frame, ensuring that every observation from Earth aligns accurately with known star positions. Observatories submit their data to the MPC, where automated algorithms compare all incoming measurements and refine the orbit with each new entry. The results are continuously updated and shared through global networks. Once an orbit is secure, researchers can determine the object's incoming velocity and direction in galactic coordinates. These values reveal not only how fast the object is moving relative to the Sun, but also where it came from. Both ʻOumuamua and Borisov entered from roughly the direction of the Lyra and Cassiopeia constellations, respectively, both consistent with the general flow of nearby stars through the Milky Way. For particularly fast-moving targets, astronomers also track photometric data measurements of brightness over time. These light curves help determine the object's rotation rate, shape, and possible tumbling motion. For ʻOumuamua, the brightness varied by a factor of 10 as it spun, implying an elongated or flattened form. For Borisov, the variations were smaller, consistent with a roughly spherical cometary nucleus. In addition to optical tracking, radar and spectroscopy play vital roles. The Arecibo and Goldstone radar facilities, before Arecibo's collapse in 2020, were capable of detecting large asteroids within a few million kilometers. But interstellar objects typically move too quickly and are too faint for radar imaging. Instead, scientists depend on spectroscopy splitting the light of the object into wavelengths to identify its composition. Specific emission lines correspond to molecules such as CN, C2, and OH, allowing researchers to confirm the presence of cometary activity, even when the object itself is little more than a dot of light. To ensure no opportunity is lost, astronomers use predictive software like JPL's Horizon system, which computes ephemeride's precise coordinates for every known small body in the solar system and beyond. When a new interstellar candidate is identified, its trajectory is uploaded immediately, allowing professional and amateur observatories alike to participate in coordinated global tracking. After the object fades from view, the data remain. Scientists continue refining the orbit, tracing its path backward to estimate the region of the galaxy it came from. For ʻOumuamua, simulations suggest it may have originated in the Carina or Perseus spiral arms, while Borisov likely came from a different stellar stream within a few hundred light-years of the Sun. None can be traced to a specific star, but the general direction and velocity align with expectations for natural ejections from planetary systems. Tracking these objects is not just about their orbits, it's also a test of our technology. Each discovery refines the tools that will detect the next one faster. The upcoming Vera C. Rubin Observatory will automate much of this process. Its data pipeline will identify moving objects in real time, calculate provisional orbits, and trigger alerts for immediate follow-up. Within hours of discovery, the world's largest telescopes and eventually, spacecraft could be tracking a new interstellar visitor before it slips away. Every successful tracking campaign adds to our understanding of how matter travels through the galaxy. From the faint streaks of light on a CCD sensor astronomers can reconstruct entire trajectories stretching across light years. The data reveal not just where these objects are going, but where they've been, how they were flung from their birth systems, and how they now thread silently through ours. For scientists, that precision is everything. The better we track them, the better we understand their origins. And as new technologies come online, the next interstellar object won't just be detected, it will be followed, studied, and perhaps even intercepted before it leaves again. Every coordinate, every arc, every image is part of a larger effort to map not just our solar system, but the movement of matter across the galaxy itself. In that data, the numbers, the trajectories, the faint traces of motion, lies the quiet proof that what we see crossing our skies began long ago. Under another Sunday, tracing origins. Where do interstellar visitors come from? Every interstellar object that passes through our solar system carries a question. Where did it begin? Each one, whether it's ʻOumuamua, Borisov, or Atlas, arrives from a direction in the sky that suggests a distant point of origin. But tracing that path backward, across light years, through the gravitational influence of countless stars, is one of the most difficult tasks in astronomy. Still, through data, mathematics, and patient reconstruction, scientists have begun to glimpse the places these travelers might once have called home. When an object like one ʻOumuamua enters the solar system, astronomers can calculate its trajectory precisely while it's within range. The challenge begins once it leaves. Gravitational interactions between stars, gas clouds, and the galactic tide slowly distort its orbit. Over millions of years, even tiny deflections accumulate, erasing any direct connection between its current motion and the system that ejected it. Yet, by combining orbital mechanics with stellar kinematics, scientists can narrow the possibilities. For ʻOumuamua, this process began within weeks of its discovery in October 2017. Researchers at the Harvard-Smithsonian Center for Astrophysics and the European Southern Observatory analyzed its inbound velocity vector, about 26 kilometers per second, relative to the Sun and its incoming direction, from the constellation Lyra. In galactic coordinates, its motion matched that of nearby stars belonging to the local standard of rest, the average motion of stars in our region of the Milky Way. This meant ʻOumuamua was not an unusually fast rogue. It was moving at roughly the same speed as the surrounding stellar population. Further modeling by Baylor-Jones et al. 2018, using data from the Gaia spacecraft, attempted to trace the object's trajectory backward in time to identify potential parent stars. The team analyzed over 7 million stellar motions, comparing each to ʻOumuamua's path. They found a handful of possible candidates, small, sun-like stars, that the object may have passed near within the past 1 to 2 million years. None provided a definitive match, but the result was clear. ʻOumuamua likely originated within the same spiral arm as the Sun, perhaps from a young system only a few hundred light-years away. For 2I, Borisov, the evidence points in a different direction. Discovered in August 2019, its hyperbolic orbit had an eccentricity of 3.36, far more extreme than ʻOumuamua's. This indicated a higher relative velocity, about 32 kilometers per second, and a trajectory from the direction of Cassiopeia. Unlike ʻOumuamua, which appeared inert, Borisov was an active comet, rich in volatile ices. Its composition, particularly the high ratio of carbon monoxide to water, suggested formation in a cold, outer region of a planetary system, beyond the equivalent of Neptune's orbit. Astrophysical models suggest that comets like Borisov are typically ejected during the planet formation phase, when giant planets scatter leftover debris. In our solar system, this process populated the Oort cloud. In others, it sends material into interstellar space. By simulating the ejection speeds of comets under various planetary configurations, researchers estimated that Borisov's departure velocity likely fell between 1 and 5 kilometers per second, relative to its parent star a typical value for such events. Tracing Borisov's exact origin is far more complex than for Oumuamua, because its higher velocity means it may have traveled tens of millions of years before reaching us. Using Gaia's second data release, scientists again searched for nearby stars whose past positions aligned with Borisov's path. None matched closely enough to claim a definitive link. But statistically, it likely came from a thin disk star system within a few hundred light-years, one with at least one large planet capable of gravitationally ejecting comets. As for 3I, Atlas, its trajectory points from the general direction of Boötes, entering the solar system at a steep inclination of nearly 50 degrees relative to the ecliptic plane. Its velocity relative to the Sun was measured at about 42 kilometers per second, consistent with other interstellar objects. Like Borisov, Atlas showed cometary activity, gas, dust, and fragmentation, implying that it too originated in an icy outer region of a planetary disk. Because of its rapid disintegration, less positional data was gathered, making precise reconstruction impossible. Still, based on its incoming vector, Atlas is thought to have come from a nearby region of the local spiral arm, possibly within 300 light-years. To understand how these ejections happen in the first place, astronomers use N-body simulations, computer models, that track the gravitational interactions between thousands of particles. These models show that when a young planetary system contains giant planets like Jupiter or Neptune, their gravity can fling small bodies outward during close encounters. If a body gains more energy than the escape velocity of its star, it leaves the system permanently. Most of these ejections occur during the first 100 million years of a system's history, when planetary migration is still violent and chaotic. This process is not unique to our solar system. Observations of protoplanetary disks by the Atacama Large Millimeter, Sub-Millimeter Array, ALMA, show that young systems around stars such as HL Tau and TW Hydrae already contain large planets forming in gas-rich environments. These systems will eventually eject billions of icy fragments into interstellar space, just as ours did. Each of those fragments becomes a potential interstellar traveler, wandering the galaxy indefinitely. Using this framework, scientists can estimate where most interstellar objects come from, not specific stars, but stellar neighborhoods. Oumuamua's motion matches the local association, a group of relatively young stars, including Vega and Altair, that share a similar galactic orbit. Borisov's trajectory aligns with the galactic thin disk, home to middle-aged stars like our Sunday Atlas, likely originated from a similar population. In short, all three appear to be ordinary material from ordinary systems, proof that the production and ejection of such objects are common throughout the Milky Way. Simulations by Porteges, Swart, and others, 2021, suggest that up to 100 trillion interstellar objects larger than 100 meters may populate our galaxy at any given time. Most will never enter a stellar system, but a few like the ones we've seen eventually will. Each carries the same story: ejected by gravity, preserved by cold, and illuminated briefly when passing through another star's light. Future detections will refine this picture further. With instruments like the Vera C. Rubin Observatory and the NEO Surveyor, astronomers will be able to calculate interstellar trajectories within hours of discovery. Combined with Gaia's precise stellar motion data, they may one day trace a visitor's path all the way back to its parent system, linking a specific comet to a specific star. That would be a first, a physical connection between worlds separated by light-years, proven through mathematics and observation. For now, we can say this much with certainty: none of the interstellar objects seen so far came from exotic or unusual sources. They came from systems much like ours, formed under the same physics and governed by the same gravitational laws. Their origins are not mysterious, they are familiar. They remind us that the Milky Way is not a collection of isolated systems, but a continuum, a galaxy, where gravity, chaos, and time work together to exchange matter across its spiral arms. The fragments we see are proof of that exchange, crossing space as quiet witnesses to a process that began billions of years ago and will continue long after ours are gone. Each one's origin is a different point in the same story, a story written not in myth or speculation, but in data, orbit lines, and light. Most surveys focus on the ecliptic plane, where asteroids and comets from our own solar system are concentrated. But interstellar objects often arrive from random inclinations, approaching from above or below that plane. Oumuamua's steep approach angle of 123 degrees was highly unusual, far outside the zone most asteroid surveys concentrate on. This means that the majority of interstellar visitors could cross our solar system without ever being imaged, simply because telescopes are not watching those regions of the sky. The third factor is speed. Typical solar system comets move at 10 to 30 kilometers per second, relative to the Sunday interstellar objects often exceed those velocities. Oumuamua's inbound speed was 26 kilometers per second, Borisov's 32 kilometers per second, and Atlas's roughly 42 kilometers per second. These fast-moving objects traverse the inner solar system in a matter of weeks. That leaves astronomers very little time to detect, confirm, and study them before they fade. Compounding this is the issue of motion blur. On a single exposure, an interstellar object's rapid movement can make it appear as a faint streak rather than a point of light. Many automated detection systems are optimized to find near-Earth asteroids, which move more slowly. As a result, faster interstellar candidates can be misclassified as image artifacts or simply missed by automated algorithms. Another limiting factor is instrument sensitivity. Most all-sky surveys operate with telescopes in the 0.51.8 meter class. These are excellent for detecting near-Earth asteroids larger than 100 meters, but they struggle with objects beyond magnitude 21-22, about 50,000 times dimmer than the faintest stars visible to the human eye. At that brightness, even large interstellar comets are effectively invisible until they're already within a few astronomical units of the Sunday. Estimates based on Oumuamua's discovery rate suggest that an object of similar size, roughly 100 meters across, passes within Earth's orbit once every few years. Yet our current surveys are only sensitive to perhaps 1 in 100 of these events. That's why, statistically, we have found only 3 in 8 years. Most surveys focus on the ecliptic plane, where asteroids and comets from our own solar system are concentrated. But interstellar objects often arrive from random inclinations, approaching from above or below that plane. Oumuamua's steep approach angle of 123 degrees was highly unusual, far outside the zone most asteroid surveys concentrate on. This means that the majority of interstellar visitors could cross our solar system without ever being imaged, simply because telescopes are not watching those regions of the sky. The third factor is speed. Typical solar system comets move at 10 to 30 kilometers per second, relative to the Sunday interstellar objects often exceed those velocities. Oumuamua's inbound speed was 26 kilometers per second, Borisov's 32 kilometers per second, and Atlas's roughly 42 kilometers per second. These fast-moving objects traverse the inner solar system in a matter of weeks. That leaves astronomers very little time to detect, confirm, and study them before they fade. Compounding this is the issue of motion blur. On a single exposure, an interstellar object's rapid movement can make it appear as a faint streak rather than a point of light. Many automated detection systems are optimized to find near-Earth asteroids, which move more slowly. As a result, faster interstellar candidates can be misclassified as image artifacts or simply missed by automated algorithms. Another limiting factor is instrument sensitivity. Most all-sky surveys operate with telescopes in the 0.51.8 meter class. These are excellent for detecting near-Earth asteroids larger than 100 meters, but they struggle with objects beyond magnitude 21-22, about 50,000 times dimmer than the faintest stars visible to the human eye. At that brightness, even large interstellar comets are effectively invisible until they're already within a few astronomical units of the Sunday. Estimates based on ʻOumuamua's discovery rate suggest that an object of similar size, roughly 100 meters across, passes within Earth's orbit once every few years. Yet our current surveys are only sensitive to perhaps 1 in 100 of these events. That's why, statistically, we have found only 3 in 8 years.